The second demonstration involves two identical 100-square-foot buildings made of sandwich panels. The only difference is in the insulating material in the panels. One has a plastic compound known as polyisocyanurate, or ISO, as the insulating material. The other uses mineral wool. Both materials are considered equal by most North American building standards.
Okay, we're going to now ignite these two buildings right now, simultaneously.
Here again, the interior temperature rises quickly, reaching 149 Celsius, or 300 degrees Fahrenheit in just a minute and 15 seconds. And more than doubling to 371 Celsius, or 700 degrees Fahrenheit, a minute and 13 seconds after that. Just 4 minutes after the fires were ignited, the ISO structure becomes involved in the fire.
And there we go. That's pre-flashover, that's called a rollover. That's called a rollover, and very soon, as the heat increases, the evaporation increases, you're getting a lot of white material evaporating off, and within seconds now, we should have the entire structure fully involved.
Seconds after Peter's prediction, the fire flashes over in breathtaking fashion. Flames, toxic gases, and smoke lash out of the opening, engulfing the entire structure. To underscore the difference between the two products, Peter conducts a simple yet dramatic demonstration of his own.
I don't know if you can see what I'm doing here, okay? This building is completely cool to the touch. I could stand here. Don't want to stand too close to that.
The smoke and toxic gases produced by the ISO insulation are numerous and lethal. Imagine the threat they pose to firefighters battling the blaze, as well as to the surrounding community. After 6 intense minutes, the firefighters move in and extinguish the fire. Peter explains the ISO fire's ferocity.
Well, in one case, you've got a contents fire. On the other side, you got a structure fire. Okay, the contents had ignited the actual structure. So now you're getting involvement in between panels. You're getting failure of the panels with cracks in between. It's a much more difficult fire tactically.
These buildings were only 100 square feet in area. Imagine the consequences for a building of over 100,000 square feet.
Well, there's an obvious comparison between the two buildings, the plastic insulation and the mineral fiber. The plastic materials that were used in here, this is very common in many structures now for exterior panels. It's obvious it's a bad choice.
Well, it's obvious that if you're building a building that has people in it, which are most buildings, I certainly wouldn't want plastic in my building. I'd want the mineral wool.
I was very impressed with the testing and the fire that we saw. The most impressive thing for me was the fact that the insulation was still cool on the outside. I'm a roofing consultant, and I'm concerned with the contribution of asphalt flowing as a liquid on fire, and the fact that it will keep the roof and the walls cooler is very interesting to me.
Codes drive the design and construction of our buildings. We put our faith in them, assuming that if a structure meets code, then it must be completely safe. Yet, when you consider the fact that the U.S. has one of the highest death rates due to fire in the industrialized world, is our faith in code somewhat blind? George Smith, a registered engineer, oversees extensive testing on a variety of materials. Many of the materials and assemblies tested already meet code.
So what FM decided to do was, because of the controversy around some of these assemblies in the United States, we put our money where our mouth is, so to speak. We ran 3 full-scale tests using non-combustible occupancy, the messy building owner mentality, and combustible roof assemblies using thermoplastic insulation. This is what it looks like about, I think this photo was taken about 7 to 8 minutes into the test. This is fully involved, of course, the exposure is fully involved. We're beginning to get fire propagation along the eaves, and we're beginning to get fire propagation within the joints in the metal deck. Now, there was another slide, or a series of slides, that I used to use with this showing progression, and you'll have to take my word for it that it didn't take much time before the numbers of combustibles and the values and the quantities of combustibles that were being generated and liberated up above caused that fire simply to roll across the metal deck. And about 12 minutes into the test, we actually said to ourselves, this is a failure. So in a 15-minute test, it took about 12 minutes or so for the fire to fully develop, and for the fire to spread 50 feet from the source. This is a product that's accepted by the building codes based on a flame spread of 25 in the tunnel, or E84 test. And if you can see what I'm showing you here, the pallet fire would be down here, the material is placed on the walls, non-combustible metal sheathing here, about 20 feet on either wall, and then out. Now the entire ceiling is involved in fire here. One of the worst things that can happen to you, there's sprinklers in this test, they haven't operated yet. They haven't operated yet because the fire spread beyond the sprinklers before they're actuated. Now, a few minutes after this photo was taken, the sprinklers went off and the fire continued to burn because the water, most sprinkler water that is, down, not up. Fire gets above the sprinkler system, races across the underside of the metal deck, or in this case, races across the surface of a reinforced plastic product that's acceptable by the building codes because it has a flame spread rating of 25 in the E84 test. This kind of an analysis demonstrates true performance in an actual fire as opposed to a synthetic environment in so many of the tests that we use today.